Hello everyone. In today's lesson we will be starting the first video in a series of videos about vectors, which is an important topic studied in the IB Math AA high level. In this full series about vectors, we will be covering the basics of vectors, the scalar product, the vector product, and how to find the angle between vectors. And after that, also we'll be studying the vector equation of lines in all forms, and equations of planes, and how to find the intersection between planes and lines. So in today's lesson we will be covering the basics of vectors. So now we will start by the definition of vectors. Vectors are defined by direction and magnitude. First, the vector notation is written like this. Here we have vector A, which is x, y. Here we have x, which is the horizontal component of vector, and y would be the vertical component. Here we have an example. Here we have vector A, as we see. Horizontally here we have a length of 4 units, and vertically we have 3. So that's why we can write the vector like this, 4, 3. Here x is equal to 4 because we have 4 units horizontally and y is 3 vertically. Now keep in mind, if we draw the same vector A here, any place here in the plane, here or anywhere else, it would be the same exact vector. So here, this vector is the same as this, not a different one. So for example, here we have a third one. These three vectors are identical, not three different vectors, as long as they have the same direction and the same magnitude. So all of these are the same vector. Now here we have other vectors here like this. For example, as we see here, for this vector we have 3 units horizontally, so that's why x is equal to 3, and 2 units vertically but downward, so that's why y here is negative 2. Another example here. For this vector, we have 4 units to the left in x, so that's why x is negative 4, because it's to the left, not right. And 2 units downward, so y would be negative 2. Now here, we have vector A. We will talk about the magnitude now. The magnitude of a vector would be the length of the vector, the length of this arrow. Here, we can find the length of this vector here, or the magnitude of this vector, by applying Pythagoras theorem in this right triangle here. So we can say that the hypotenuse here, or the length of the vector, would be under the square root 3 squared plus 4 squared. Here we apply Pythagoras theorem, which is 5. So the length of this, or the magnitude of vector A, is 5. Here, this notation means the magnitude of vector A. So generally speaking, the magnitude of any vector here like this, it would be under the square root x squared plus y squared. This is basically Pythagoras theorem. Now let's move on to vectors in 3 dimensions, or vectors in 3D. Which is what appears in IB exams. Vectors in 3D can be written like this, x, y, z. So here we have the z component, which is the height of the vector, as we will see later in the illustration. Similarly to vectors in 2D, the magnitude of vector A would be x squared plus y squared. Here we have plus z squared as well, under the square root. Basically, this is Pythagoras theorem in the space in 3D. Here now we have an example. We have vector A, which is 4, 6, and 5. Here z is equal to 5. If we illustrate this vector A here in 3 dimensions, it will be like this. Here we have the x-axis and the y-axis, and here we have the height, or the z-axis. Vector A is illustrated here. Now, as you see from this point in the vector, if we drop here a line perpendicularly to the xy plane, and then we go to the x-axis here, x would be 4. So that's why here we have x4. Then, if we go to the y-axis here, it would be 6, as we have here. And if we go from this point to the z-axis here, it will be 5, so z here is 5. This is the position vector of A as it starts from the origin 0. We will talk more about position vectors shortly. So now, when we calculate the magnitude of this vector A using this formula here, we will have the magnitude of A will be these components squared, 4 squared plus 6 squared plus 5 squared under the square root, which is the square root of 77. Now keep in mind that we might see vectors written in different notation in some textbooks. So for example here, you might see the same vector A here written in this notation, 4i plus 6j plus 5k. Basically here, this is the x component 4 and the y component 6 and z is 5. So it can be written in this notation here, which is better and simpler. 4 and 6, and here we have 5. This IJK notation is not used in the IB exams anymore, so this is better and easier. Now here we'll move on to the next idea, which is the opposite direction of vectors. Let's assume that we have vector A, which is 3, negative 4. If you calculate the magnitude of this, which is under the square root 3 squared plus negative 4 squared, the magnitude would be 5. And now, if we illustrate this vector A here, it will be like this. As you see, 3 on x, negative 4 on y as it's going down, 4 units. Now, what happens if we multiply this vector A by negative 1? Here, when we multiply by negative 1, we multiply each component here by negative 1. So we have 3 times negative 1, and negative 4 times negative 1 will be 4. If we calculate the magnitude of this vector A here using the magnitude formula, we would also obtain 5. So these two vectors have the same magnitude, but negative A has an opposite direction of A because we multiplied by negative 1. If we illustrate negative A here, as you see, we have negative 3 on x to the left and 4 on y. It's the same magnitude A in terms of length, both have the same length 5, but opposite direction. Similarly now, in 3D vectors, here we have vector A. When we multiply by negative 1, it will be negative 4, negative 7, and 5. These two vectors have opposite directions. Now let's move on to the idea of position vectors. First, what are position vectors? What makes them like position vectors? They have a starting point at the origin 0, 0, 0 and an end point at any point A, x, y, z. It could be any point in the space. So here they are useful because they tell us the instantaneous position of any point with respect to a fixed point like the origin. So that's why we call them position vectors. So they start from the origin and we can write it like this. Here, vector A, which is the position vector of point A that starts from the origin O and ends at A, we write it like this, O, A. O here represents the starting point and A is the end point. Or we can write it simply like this, little a. It's x, y, z, the same as this point, but we write it in vector form. So here, for example, the position vector of the point 2, 4 in 2D can be written as OA, which is 2, 4. It's the position vector of A that starts from the origin, as we see here, x is 2 and y is 4. Similarly, in 3D, the position vector of this point here, B, which is 2, negative 5 and 7, can be written like this, little b, 2, negative 5, 7. We write the same point, but in vector form. So now, after we studied position vectors, we'll move on to an important idea, which is how to find the vector between 2 points. Let's assume that here we have 2 points in the space, A and B. We need to find the vector AB that connects both. This vector here, as we see, starts from A and ends at B. Basically, to find the vector AB, it's easy. We do it like this. The end point B minus the beginning point A. So we do here B minus A like this. So vector AB, or from A to B, can be done like this. First, we write it as a vector, of course. It will be x, which is 9, minus x, which is 5. So here, B minus A. Then 6 minus negative 4, which will be 10 later. We have here 1 minus 2. So when we simplify it, we have here 4, 10, and negative 1. Here, 6 minus negative 4 will be 6 plus 4, which is 10. So basically, we do the end minus the beginning. And now to understand why, here we have the position vector of A and B illustrated. Now both are position vectors. So they start here, as we see, from the origin 0. The vector AB that's wanted here, it's this. It starts from A and ends at B. So how do we find AB here? How do we find the vector AB? As you see in vectors here, to go from point A to point B, first we go from A to O, and then from O to B. So as we see here, to go from A to B, first we have AO plus OB. So from A to O now, as we see, from O to A, it will be A, little a. So when we go in the opposite direction from A to the origin, it will be the opposite of A. That's why we will write it like negative A. Then when we go from O to B here, from O to B, it will be positive B because it's in the same direction. And this negative A plus B can be rewritten like this, B first minus A. So that's why here, when we do it like this, we do B minus A. Now we will study the operations with vectors. With vectors, we can do addition, subtraction, or multiplying by a scalar. First, we will start with the addition. When we add two vectors like these, we just add the corresponding elements, 5 and negative 3, negative 2 plus 8, 11 plus 2. So here, 5 and negative 3 will be 2, and then we have here 6, 11 plus 2 will be 13. When we illustrate this, here, when we add two vectors like this and this, then the resultant vector, or the sum of the two vectors here, is called the resultant, which is the sum here that we got. It's a new vector that starts from the beginning of the first one and ends at the end of the second vector. So this is here the sum or the addition of the two vectors. Now subtraction can be done in the same way here. We subtract the corresponding numbers. So first we do 5 minus 2 here, which is 3. 7 minus 9, negative 2. Negative 3 minus negative 4, which will be positive 1. Next now, we have multiplying by a scalar. So here, we have a vector 5, negative 3, and 4. We can multiply this vector here by any non-zero number or constant number, or we call it a scalar, which means it's just a fixed number, not a vector. Basically, we multiply the number 2 here by each component here. So we have 2 times 5, which is 10, and 2 by negative 3, which is negative 6, then 2 by 4, which is 8. Now here, when we multiply any vector by a non-zero number, we get a new vector that's parallel to the original vector. So this vector here and this one are parallel in the space if we draw them. We will get to know these like parallel vectors in the next video about vectors, when we study parallel vectors and unit vectors. I hope that you have found the video helpful. Please consider subscribing, and thank you for watching.